This is a trip to the moon, calculus with parametric and polar equations, part 3, go for TLI. In part 2, we did some calculations to prepare for TLI, the Translunar Injection Burn. That's the term for entering into an elliptical transfer orbit to the moon. At the initial circular orbit above the planet Kerbal, at an altitude of 100 kilometers, our velocity was 2,246 meters per second. We determined in part 2 that in order to reach the Mun, we would need to increase our velocity to 3,087 meters per second. That's a delta V of 841 meters per second to follow an elliptical transfer orbit to the Mun's altitude at 11,400 kilometers. A graph of the planned transfer orbit looks like this purple curve. This is the elliptical transfer orbit that we're going to follow to get out to the Mun. The Mun is the moon of the planet Kerbal. So Kerbal has a radius of 600 kilometers. That's this inner circle. And we're at a 700 kilometer radius orbit that is 100 kilometers above the surface of Kerbal. And the transfer orbit that we're going to follow has a semi-major axis of 6,350 kilometers and an eccentricity of 0.8898, two values that were calculated in part 2 of this series. So our apoapsis is out here at 12,000 kilometers from the center of Kerbal. So this is the apoapsis and the periapsis being the closest point on that transfer orbit. So in this part 3 of the series, we'll compute the phase angle for the translunar injection burn. That's sort of basically timing when to begin the rocket burn, the injection burn. We'll compute the slope of the tangents to the flight path along this orbit. We'll compute the flight path angle also, which also referred to as the pitch. And we'll compute the angle during orbit. We'll check all those results in the game Kerbal Space Program. The phase angle is the angle between the spacecraft's position in its orbit and the Mun's position in its orbit. So the phase angle is this angle here. So the rocket might be starting at this point here. That would be the periapsis when it fires its rockets to travel on this transfer orbit. At that moment, we're looking for the phase angle at that moment. So the Mun is at this position right here, P0, at the time of the transfer, the translunar injection burn. That's where the Mun is at when the spacecraft fires its rockets. And then it's going to intercept the Mun here at position P1 after completing that transfer orbit. So in part 2, we determined the period of a complete elliptical orbit from Kerbal to the Mun and then back again all the way around the ellipse with a semi-major axis of 6,350 kilometers or 6,350,000 meters. If it's 6,350,000 meters, that period for the complete orbit was this quantity 2 times pi times the square root of the semi-major axis cubed over the gravitational parameter with a semi-major axis of 6,350,000 meters. Cubing that, dividing by a gravitational parameter based on the mass of Kerbal and the universal gravitational constant, 3.53 times 10 to the 12, putting those two g and m together gives you this value. Well, the complete elliptical orbit is 53,512 seconds. This is the time for a complete orbit around the ellipse. And interesting, it doesn't depend on the eccentricity, right? The eccentricity doesn't figure into the calculation. So the transfer orbit from Kerbal to the Mun will take half of this time. That is 53,512 divided by 2, or 26,756 seconds. And 26,756 seconds is about 7 hours 25 minutes. We can look for that in the game to see if our orbit's expected to be about 7.5 hours. Our transfer orbit to the Mun is about 7.5 hours. Took about 3 days for the Apollo spacecraft to travel from the Earth to the Moon. So we realize that the Kerbal Mun system is on a much smaller scale. Now the Moon orbits around Kerbin at 542 meters per second. And during the 26,756 seconds of the flight to the Mun will travel at this rate for this period of time a total of 14,501,752 meters in an arc of a circle. Because the Mun orbits around Kerbin in a circle with a radius of 12 million meters and will complete an arc of S equal to 14,501,752 meters during the rocket's flight to the Mun, the angle theta that the Mun will sweep out during the rocket's flight is given by this theta equal S over R. That's basically the formula for the angle in radians when you have this arc S and this radius R for a circle. So that is the angle theta in radians, 1.21. Converting that here to degrees so we can kind of better visualize that, 69.2 degrees, and it's more practical often in this kind of context to use degrees. And so actually the phase angle that we're interested in, if we're at a position here with the spacecraft, we'll have to take 180 degrees for this entire axis. Take 180 degrees minus the theta that we just computed to get the actual phase angle phi, about 110.8. So we conclude that the translunar injection burn must occur at a phase angle of about 110.8 degrees. That is, in other words, the Mun needs to be about 110.8 degrees ahead of the rocket in its orbit around Kerbin when we initiate that translunar injection burn. Let's take a look at see how that looks in the game. Now we wait for the maneuver node to fire the rocket's prograde in the direction we're traveling for a delta V of 841 meters per second. We'll watch the velocity increase to 3,087 meters per second, and after the burn we'll check the speed, semi-major axis of our orbit, the eccentricity, and the orbital period to make sure that we're on course to intercept the Mun. We'll take a look at all these values over here on the right hand side. I know they're really small, so I'll try zooming in on them so hopefully you'll be able to see them. The countdown to the maneuver node is down at the bottom of the screen here, and then another really kind of neat thing to look for is just after the rocket burns, you'll be able to see the Mun rise above the limb of the planet Kerbin. And it's kind of a neat scene. Okay, looks like we got up to about 3,085 right there. That's pretty good, close to the target. Now looking over on the right side of the screen, we see some flight data. The apoapsis height is 11,640 172 kilometers, very close to our plan of reaching the Mun at 11,400 kilometers. And we have time to apoapsis. Now, Kerbin days are 6 hours, so a 7.5 hour trip is 1 day, 1 hour and a half hour for Kerbals. So that's very close to what we would expect. The eccentricity of this orbit is 0.89, very close to our planned trajectory. Also in part 2, we had computed the speed at apoapsis of 180 meters per second. Now this path that we're currently on takes us a little bit further, so that speed that we see at 172 meters per second at apoapsis is just what we should expect for this orbit. Now the next thing we can look at is to find the slope of any tangent to the flight path given the orbital path in polar form. We'll do a derivative. So we're going to find dy dx as follows. So this is the polar form of the elliptical orbit. R is a function of theta. The A is the semi-major axis. It's a constant in the context here. Let's have the A fixed and the eccentricity. This is E, the eccentricity of the orbit. So what we're going to look for is really dy dx. And so in order to get that, I have to basically convert to rectangular coordinates. So I'm going to write y as a converting from polar. The y value in the xy plane would be r sine theta. So r now is a function of the eccentricity and the semi-major axis and the angle theta. So this is r right here, r times sine theta. That converts to the y value in the xy plane. So I'm about to do a derivative, so I'm going to write this a 1 minus e squared as a constant factor here. And then this 1 plus e cos theta, I'll just write that with a negative 1 power so that it makes the derivative easy. So I don't really have to do quotient rule here. I'll just turn it into a product rule because this stuff that's right here, this is just a constant. So taking a derivative of y with respect to theta can treat this a 1 minus e squared as a constant. It doesn't change with theta. And so the negative 1 is going to come in front, subtract 1, take a derivative of the inside, that's the chain rule. Derivative of cosine is minus sine. And then this sign here, this is because I'm doing product rule. I'm doing product rule with these two factors. So I'm doing the derivative of the first factor, all of this stuff, times the sine, plus now the first factor times the derivative of sine. That's the cosine. So once I've got those two terms, I'll write them back as fractions, get a common denominator, combine the numerators. One thing that's kind of neat here is that there's an e sine squared and e cosine squared. So you can factor out e. Sine squared plus cosine squared is equal to 1. So you just get e plus cos theta. This is e, the eccentricity, right? Not the number e. Okay, so that's dy d theta. Now we'll do the same thing for dx d theta. So to convert into rectangular coordinates, the conversion formula is r cos theta to get the x value. So this is r again times cos theta. I'll do the same thing I did with y. I'll just write this a 1 minus e squared as a constant. Bring this denominator up here as a minus 1, and the cosine there is at the end. Now it's just really just product rule with these two factors. So the constant gets copied times the negative 1 goes down, copy the inside, subtract 1, take a derivative of the inside, derivative of cosine is minus sine, and it's times the cosine, the other factor, plus the first factor times the derivative of cosine. Write those as fractions, get a common denominator. Let's see what happened here. E sine theta cos theta minus e sine theta cos theta. That's kind of a nice, convenient little canceling right there. It leaves you just negative sine theta in the numerator. Okay, so if I have dy d theta here and dx d theta there, so I can find dy dx. This would be the slope of the tangent to the path in the xy plane. The dy dx is dy d theta divided by dx d theta. So this is dy d theta on top, dx d theta on the bottom. When I divide, isn't that cool how the a 1 minus e squared cancel out? Actually, the 1 plus e cos squared on the denominator here, both of those cancel out, and there is my result. E plus cos theta over negative sine theta, which I could leave this way or that way. this represents the slope of the tangent to the elliptical path in the xy plane. That's the dy dx, the slope of the tangent. It's the direction of the velocity, right? This formula is the slope of the tangent to the orbital path at any point on that path. That slope would represent the direction of velocity in the orbital plane. This slope represents the change in y with respect to x for the spacecraft's path in the xy plane, and it's written really only in terms of the true anomaly. The eccentricity is fixed. The true anomaly is that angle that you sweep out as you go through the orbit. So this is the slope as a function of the true anomaly theta. Of course, it also depends on the eccentricity. So that's the slope of the tangent. What's kind of neat, special case, if the eccentricity was 0, the orbit is circular, and the slope of the tangent to a circular path is given by, well, if e is 0, this cancels out, you get negative cotangent theta. Right, so this is a circular orbit, a circle, and that's the true anomaly theta. And as that rotates around, this line here has a slope that's equal to the tangent of theta, and this is perpendicular. Its slope is negative cotangent theta. So negative cotangent theta gives you the slope of a tangent to the circle as a function of that angle theta. In part 2 of this series, we calculated that the transfer orbit to the Mun is an ellipse with an eccentricity of e equal 0.8898. So we can now find the slope of the tangent to this orbital path, for example, at any point, for example, when the true anomaly is 90 degrees. So if the eccentricity is 0.8898 and the true anomaly is 90 degrees, the slope of the tangent in terms of dy over dx is minus the eccentricity over sine of 90 degrees plus minus cotangent of negative 90, right? I'm using this formula right here. Minus the eccentricity over sine theta minus negative cotangent theta. So plugging in the eccentricity and a particular angle that might be of interest, sine of 90 is equal to 1, cotangent of 90 is equal to 0, and so we end up with exactly the eccentricity or the negative of the eccentricity. Interesting that right at that point when this true anomaly theta is 90 degrees, when you've gone from periapsis to an angle of 90 degrees, that point right there, the slope of the tangent at 90 degrees is just exactly the negative of the eccentricity of the ellipse. We can sort of test that out here in Geogebra. So this is the Mun's orbit out here, this big circle. Kerbal is the small circle in there. And we just began on this orbit from an altitude of 100 kilometers above the surface, right there, traveling up in this direction with an increasing true anomaly. Right now in this, it's 45 degrees, about 45.8 degrees. You can see the true anomaly showing up right here. This is the eccentricity of this particular path, 0.8895 if you round off. So not precisely the same, but 0.889, very close to what I intended. And so what I'm interested in is actually the slope of this tangent at a true anomaly of 90. So if this reaches about 90, I got a slope here, 0.888. So yeah, I think that's pretty convincing that that's, I'm not going to, the way I set this up, it's just not going to be exact. But it's pretty convincing that at 90 degrees, I get a slope that pretty much matches the eccentricity very closely. In this, numerically, we're very close. So that's pretty good. That's kind of neat. That's a little discovery there about the nature of an ellipse. Now we can use the slope of that tangent in this case right now to find what we call the flight path angle. And the flight path angle is the angle between the velocity and the horizon. So in this case, when you're right at 90 degrees true anomaly, the horizon is horizontal in the xy plane. And so we can really just get the slope of this line in the xy plane and then find that angle that I called alpha in this work here. I call alpha the flight path angle. It's the angle between the horizon, which is a line here parallel to the horizon drawn down here. So if the slope of this line is actually negative 0.889, I can say go forward 1 unit and down 0.8898 units, or you could go over 1 and then, or you could say, let's say, down 0.8898 and over 1. So this triangle right here has alpha, the flight path angle, in this right here. This is that flight path angle. So we could just take the tangent of that that value, that slope. The tangent of that slope is about 42 degrees. So that should match the pitch in the game at that instant. Another thing that we could actually check in the game at that moment that we hit 90 degrees true anomaly, we could compute the altitude at this particular point, because we have the r for the polar form of the orbit. So we'll put in the semi-major axis 6350. The eccentricity will use the true anomaly of 90. So we get a 1,322.425 kilometer, or about 1,322,425 meters. That's the radius of the orbit, but actually the altitude, if you subtract out the radius of Kerbal, the radius of Kerbal is 600,000 meters. So subtracting out the 600,000 meters, we should see about 722,425 meters as the altitude at that instant. So we'll be checking all these things. True anomaly 90, we should about 722,000 meters and about a pitch of 42 degrees. Let's see if that happens. We can also see the pitch right here on the nav ball, that it's just above 40 degrees, about 42 degrees, and of course the heading at 90 degrees we can see in the nav ball. Another point of interest on the flight path is when the slope of the orbit is 0 in the xy plane. This point here, where the velocity vector is horizontal in this xy plane as I've drawn it, the slope then would be 0. So if this is my formula for the slope of the tangent, eccentricity plus cosine of theta, the true anomaly, divided by minus sine of theta, we'll look for the value of theta when dy dx is 0. So we'll just set that equal to 0. That's a fraction. It's only 0 and the top is 0. So if you solve, you got cosine equal negative e, the eccentricity, negative of the eccentricity. So you can solve for theta with the cosine inverse. So cosine inverse of negative e, well, whatever the eccentricity is would change for different ellipses. So this particular ellipse, we have an eccentricity of 0.8898 in our sort of theoretical planned trajectory. So if I'm using that value for the eccentricity, I'm getting about 152.8 degrees. Now the actual path that I'm flying in the game, it wasn't precisely 0.8898, so I won't expect exactly 152.8 as the true anomaly when this happens, but something around that, around 152 degrees or 153 degrees. I will look for a horizontal flight path, slope of the velocity vector in the xy plane to be horizontal around that angle. So right about this point, when this angle here, theta, is 152.8, the velocity vector is horizontal in the xy plane, and that means this is once again a specific point where I don't have to do anything really fancy to figure out the pitch or flight path angle. What is that flight path angle? We can determine the flight path angle this time because the velocity is horizontal in the xy plane of the orbit as drawn here. So the flight path angle, also called the pitch, is the angle between the velocity and the horizon. Since the velocity is horizontal here, we can subtract 90 from the true anomaly to get the flight path angle. Basically, you could see sort of in this diagram, if the true anomaly is this angle theta, then it's the same by vertical angles as this angle I'm tracing out right here. So if you minus the 90, you'll get what's left here, the pitch. It should be about 62.8, maybe 63. It, again, won't be exact because I don't have an eccentricity of exactly 0.8898 as the trajectory that I'm flying in the game. But let's see how close it is. Oh yeah, one more thing before we go back to the game. We can actually compute what the altitude should be at that point. Right? So we can compute the altitude at the instant the flight path has 0 slope. When the true anomaly is 152.8, we get the radius of the orbit using our polar equation for the orbit with an eccentricity, if I say theoretically 0.8898, true anomaly 152.8, it should be about 6339 kilometers, which is 6,339,609 meters, 6,339,609 meters, and subtracting off again the radius of Kerbal to actually get the altitude, roughly 5740 kilometers. So what I'll be looking for is a true anomaly of about 153, altitude about 5740 kilometers, and a pitch of about 63. Let's see if that works. Suppose I could also go quick back to Geogebra and take a look at this orbit, and if I bring this out to about 152, that's about where the slope is 0. 153, slope is 0. Yeah, that's it. That's the point where the slope is 0 in the xy plane of the orbit. If I use the orbital plane as an xy plane, slope is 0 at that point at 153 roughly degrees for the true anomaly. Finally, it would be interesting if we could develop a formula to compute the flight path angle at any point along the orbit. So here's the radial vector that locates the position of the spacecraft, let's say at point 1. So here's the velocity tangent to that curve. And the angle, the flight path angle phi, is the angle between this perpendicular to the radial vector and the velocity. So the angle between the velocity and basically the horizon. In this diagram, the angle phi is the flight path angle. It's the angle between the velocity vector v and the horizon. And in space, the horizon is equivalent to the perpendicular to the radial vector r. Consider 2 points P and P' that are close to each other along the orbital path as shown here. The quantity dr right here represents a change in the radial position as the spacecraft moves from P here to P', and the value of r changes from this value to r1. At the point P, we consider the triangle made of sides dr and r d theta. That quantity r d theta is the arc of a circle with radius r that subtends the angle d theta. So note that the tangent of phi, this angle right here, is the opposite over the adjacent, approximately. It's not precise because there's this obvious little gap here. Right? R1 is the entire distance from the center of Kerbal out to that point P'. And so the differential in R is that change in the length of the radial vector. And the tangent of phi is the opposite side of this triangle divided by the adjacent side. So dr divided by r d theta, as I have written here, dr divided by r d theta. And that's an approximation for the tangent of phi. That approximation is pretty good when r d theta and dr are pretty small, and then this little gap is pretty small. But this expression, dr divided by r d theta, can be written as 1 over r dr d theta, and as both dr and d theta approach 0, that approximation becomes exact at the point P. So we're computing the flight path angle phi at the point P using this fraction 1 over r dr d theta. Okay, so to find the flight path angle, given r equals a times 1 minus the eccentricity squared over 1 plus e cos theta, if that's the formula for the position r, we can compute 1 over r dr d theta and then do a tan inverse of that. So if this is r equal to a times 1 minus e squared over 1 plus e cos theta, that's the polar form of the ellipse, I'm going to write this 1 plus e cos theta here with a negative 1 power because I'm about to do a derivative with respect to theta, and this is all constant with respect to theta. The semi-major axis and the eccentricity don't change when you change the angle, the true anomaly. So that's a constant. The negative 1 goes in front. You're going to subtract 1, the power rule, take a derivative of the inside. This e is a constant. Derivative of cosine is minus sine. So rearranging that, these negatives, they cancel out, give me this factor here, and this is dr d theta, the rate of change of the radial position with respect to the angle theta. And so if you want to do 1 over r dr d theta, this is the reciprocal of r, right? R was this expression. Since I have 1 over r, I'm just flipping it. The 1 plus e cos theta, that goes on top. In the a 1 minus e squared, that went on the bottom. So that's the 1 over r right there times dr d theta that we just computed here, and the a times 1 minus e squared, that cancels. The 1 plus e cos theta, that's going to cancel with one factor that I had since there was a square. And so yeah, this is a formula now for 1 over r dr d theta, and so the tangent of the flight path angle should equal this value. So we can find the flight path angle at any angle theta by taking a tan inverse. So this is a formula for the flight path angle. it's kind of neat. You can actually now go back and check. We can confirm our previous calculations for flight path angle at some specific points, like when theta was 90 degrees, plugging in 90 degrees for theta with the eccentricity that we have for our sort of model for the path. That's tan inverse of 0.8898, just as we were computing. 42 degrees. And at that point 152.8, where we were at the sort of the turning point in the path, when the velocity was horizontal in the xy plane, at an angle of 152.8, we're going to do the tan inverse of about 1.9498. That's about 62.8. That's exactly what I calculated directly in that particular example, just based on the geometry of the situation. So, and we can confirm now that that 62.8 was basically the maximum in the model. I know it hit about 63 in the game, but that's because I didn't have exactly the same eccentricity. So we can confirm from the graph of phi. Here I am graphing where was this Desmos. I couldn't use E as a different, as a parameter. So I used C for the eccentricity. I set it to 0.8898 and graphed the flight path angle and found a maximum. So probably in practice we would only think from 0 to 180 and then start again on the other part of the trajectory back to the planet. But yeah, we can confirm from this graph that the maximum flight path angle is at 62.8, and this occurs when the true anomaly is 152.8. This is the point where in the orbit where when the slope of the tangent in the xy plane is 0, and it's the point when the spacecraft is kind of turning, in a sense, toward the Mun in its orbital plane. One other thing that's kind of fun here, what do you think will happen if I move the eccentricity back toward closer to 0, where you have a circle and the spacecraft would be just orbiting in a circle? What would the flight path angle be at that point when you're always perpendicular to the radial vector as you go around the circle, go around the planet in a circular orbit? So think about what would happen, and I'll drop this back towards 0. You get closer and closer to a pitch of 0, a flight path angle of 0. That is, the angle between the velocity and the horizon is always 0. The angle between the horizon and the velocity is always 0. It's 90 degrees between the radial vector and the velocity. So if I move back to a circular orbit here, put the two foci at the same point, I get a circular orbit. Now, the angle between the radial vector and the velocity is always 90 degrees, but the angle between the horizon and the velocity is always 0 degrees. So there's always a 0-degree pitch if you're in a circular orbit. So that's what we're seeing there. And as the eccentricity increases, that flight path angle changes. It's another interesting topic to think about, but I've probably gone on long enough with this. So let's get back to what I was doing.